Chapter 9 is circles. So the first section, we're going to look at the parts of a circle: the center, the radius, diameter, chord, secant, tangent. Section 2, we're going to look at tangents. We're going to have tangents to circles. We're going to have internal and external tangent lines, and then we're going to have internally and externally tangent circles. We're going to look at arcs and central angles, relationships between arcs. An arc is a part of a circle, not just the noise that a seal makes. Um, Arcs and chords, the relationship between arcs and chords in circles. We're going to look at inscribed angles. Scribe is to draw, to write. So that is to draw inside of a circle. Other angles, we're going to look at circles and the lengths of segments. That's if two chords intersect inside of a circle, then the product of the segments of one chord is equal to the product of the segments of the other. And things like if two secants, two tangents, or a secant and a tangent are drawn to a circle from a point outside of a circle, then the product of one secant and its external segment, that kind of stuff. It's a bunch of stuff about secants and tangents drawn to a circle from a point outside. We'll get to that in due time. We have the odd answer solutions and then the study guide. So we're going to jump right into Unit 9.1, looking at the parts of circles. So parts of circles and spheres. A circle by definition, again, a definition tells us how to draw something. So a circle is the set of all points in a plane, a given distance from a given point in that plane. Circle, the set of all points in a plane, a given distance from a given point in that plane. Let me make my pen right. The set of all points in a plane. See, that makes it flat. The set of all points in a plane, a given distance from a given point in that plane. Now, example, if we took a given point and a given distance, and we found all of the points in the plane, a given distance from a given point in that plane, the set of all points in the plane, a given distance from a given point in that plane makes a circle. Tells us how to draw a circle. The given point is called the center, and the center was point A, which we could write as PTA. The given distance, that all of those points were the same distance from the center, is the radius. So the radius is the given distance. But that's not really the formal definition we want. If we look at how to draw the radius, then it is a segment from the center to a point on the circle. A segment from the center to a point on the circle. Again, it was that given distance, or we might even say it's halfway across the circle. So it's half the distance across the circle. It is that given distance that we talked about, or we can say it's a segment from the center to a point on the circle. Okay? So the given distance, whoops, the more formal definition, a segment from the center to a point on the circle, or the way we use it as we're calculating, it's halfway across the circle. Okay? We're going to name some radii. The plural of radius is radii. One radius is AB. There's another radius from A to C. And there's another radius from A to D. A radius is a segment from the center to a point on the circle. It's the given distance, or it's halfway across the circle. Okay? A chord. A chord is a segment that joins 2 points on a circle. A segment that joins 2 points on a circle. I think of it like a trot line chord. I'm just an old fisherman. So if we took 2 points on a circle like point E and point F, and we join those, stretched a line across there, that's a chord. Okay? A chord is a segment that joins 2 points on a circle. Well, EF joins 2 points on a circle, but the diameter also is a segment that joins 2 points on a circle. So the diameter is also a chord. It's a chord that passes through the center. HG is also a chord. So we had 3 chords in the circle. So a circle is a set of all points in a plane, a given distance from a given point in that plane. The given point is called the center, and the given distance is called the radius. A chord is a segment that joins 2 points on a circle. A diameter is a special chord. It's a chord that passes through the center of the circle. So a diameter is a chord that passes through the center of the circle. That's the formal definition. It's all the way across the circle is the way that we think about it as we use the formulas, the distance across the circle. So the radius is half the distance across the circle. The diameter is the entire distance across the circle. The formal definition of a diameter is a chord that passes through the center of the circle. Remember that a definition tells us how to draw something, but all definitions have to be based on other definitions, postulates, and theorems. So it's a developmental process in the language of geometry. Okay? A secant. The way I kind of remember a secant is, I guess, kind of weird, but anyway. I think of a chord like a trot line cord going across a pool. You'd put a stake in each end and stretch the cord. So a chord is a segment that joins 2 points on a circle. And so I think of this as water in my circle. And a secant is a line that intersects a circle in 2 points. So the secant keeps on going where the chord stops. And so I say it goes through the sea, the water, and it can't stop. So the secant is the line, and the chord is the segment. So a secant is a line that intersects a circle in 2 points. A secant is a line that intersects a circle in 2 points, or a line that passes through the circle. So here's the formal definition, and here's what you're going to see with your eyes. It goes through the sea, and it can't stop. And so a secant there was line HG. Line HG was our secant. Okay? tangent. A tangent is a line that lies in the plane of a circle and intersects the circle in one point. Now, it means it's not coming in here crooked. It lies in the same flat surface as the circle. So it's a line that lies in the plane of a circle and intersects the circle in one point. That point at which that tangent line intersects the circle, we call the point of tangency. So line IJ is a tangent to the circle, and point I is the point of tangency. So a tangent line is a line that lies in the plane of a circle and intersects the circle in one point. A tangent is a line that lies in the plane of the circle and intersects a circle in one point. We said the tangent line in the circle above was line IJ. That point at which the tangent line intersects the circle is called the point of tangency. It's on the outer surface of the circle. Okay? Remember the definition of a circle, the set of all points in a plane. That makes it flat. A given distance from a given point in that plane. Well, if we take out the phrase in a plane, that means that we could take a given point and we could go north, south, east, west, northeast, southwest. We could go any direction and it doesn't have to be flat. So every point equidistant from that point, every point equidistant from that point, not limited by being in a plane, would create a sphere. A sphere is the set of all points a given distance from a given point. The set of all points a given distance from a given point. Again, if we insert in a plane, it makes it flat and we have a circle. Okay? The given distance is called the radius again, and the given point is called the center again. So the center would be the given point, point A. The radii would be from the center to a point on the sphere, a segment from the center to a point on the sphere. So the radii would be AB, AC, AE. There's also AF that we could have named as a radius. The diameter is a chord that passes through the center, so the diameter is BF. A chord is a segment joining 2 points on the sphere, so the diameter BF is a chord that passes through the center. We also have a point G and a point F, and that segment that connects them, GF, is a chord. A segment joining 2 points on the sphere. A secant would be a line that intersected the sphere in 2 points. It went through the C and couldn't stop. Line GF. A tangent lies in the can't lie on the plane of the sphere, can it? A tangent to a circle is a line that lies in the plane of a circle and intersects the circle in one point. A sphere is three-dimensional, so a tangent to a sphere would simply be a line that intersects it in one point. And so we can say that line CD is a tangent to sphere, A. Line CD is a line tangent to sphere A, where point C is the point of tangent C. Okay? Now, the thing that gives a sphere its size is its radius. The thing that gives a circle its size is its radius. All circles are the same shape and all spheres are the same shape, so it's kind of given that they're the same shape. In other words, every circle is similar to every other circle, and every sphere is similar to every other sphere. But to be congruent, the radii have to be equal because that's what gives them their size. So congruent circles or congruent spheres have equal radii. And again, radii is plural for radius. Radius is singular, okay? Concentric circles. Now, they actually look like a target, see? But concentric circles are circles in the same plane with the same center. Circles in the same plane with the same center. One of the most familiar places we see concentric circles, besides in a target, is if you threw a rock in the water and the waves started going out in all directions, and you might could see those little waves rippling out in a concentrical circle concept. Concentric circles are circles in the same, I left out the plane, did concentric circles are circles in the same plane with the same center. In other words, we're not going to have a circle like this with this center and then a circle that, this is going to be a little bit hard to draw, was like that had the same center, to where when you put them together it was three-dimensional like a sphere. Those are circles that have the same center, but they're not in the same plane, so they're not concentric circles. Concentric circles are flat. Okay? Now, spheres are three-dimensional, so all we have to say there is they're spheres with the same center. Spheres with the same center. Okay? Concentric circles are circles in the same plane with the same center. Concentric spheres are spheres with the same center. So now we're going to talk about inscribed and circumscribed. If you're a student of the Bible, then you would know a scribe is one that wrote down, uh, copied the biblical text or copied the Old Testament. So they would pass it down from generation to generation by writing because they didn't have copy machines. So a scribe is one that writes or draws. And in, that means to draw in. So if a polygon is inscribed in a circle, if it's drawn inside the circle. A polygon is inscribed in a circle, and the circle is circumscribed. That means it's drawn around. Circum is circle, scribe is draw, circumscribed is draw around, draw, circle, draw around. So polygon is inscribed in a circle, and the circle is circumscribed. About the polygon, when each, see this polygon that's inscribed? When each vertex of the polygon lies on the circle. So we say that a polygon is inscribed in a circle, and the circle is circumscribed about the polygon. It's if each vertex of the polygon is a point on the circle. We say that a polygon is circumscribed about a circle, and that the circle is inscribed in the polygon. Let me do a better job there. If each side of the polygon is a tangent to the circle, meaning it lies in the plane of the circle, it intersects a circle in one point, and each of those points then would be a point of tangency. A polygon is said to be circumscribed about a circle, and the circle is inscribed in the polygon when each side of the polygon I got the polygon twice. When each side of the polygon is a tangent to the circle. Okay? So if the polygon is inscribed, each vertex is a point on the circle. If the polygon is circumscribed, then each side is a tangent to the circle. We're on definition number 53 for the year. Can you quote them all word for word? You need to be able to. Hopefully you can quote every single definition, postulate, and theorem word for word. You need to be able to do proofs and to be able to use your geometry and the applications that are coming in college algebra, college trig, in engineering or physics or whatever's coming down the road for you. Okay? All right, daily work unit 9.1. Name a circle. A circle is a set of all points in a plane, a given distance from a given point in that plane. We name a circle by making a circle symbol and using its center, and so we can call that circle I. Again, a circle is a set of all points in a plane, a given distance from a given point in that plane. The given point is center, so the center of the circle is point I, and the given distance is called the radius. It's a segment from the center to a point on the circle, or it's half the distance across the circle. It is a segment, and so we will name the radius as a segment. There's one of them. You can name the rest of them. Name 4 chords. A chord is a segment that joins 2 points on a circle. One chord would be segment NT. You can name some others. The diameter is a chord that passes through the center. A chord that passes through the center is segment BM. Name a secant. A secant went through the C, but it didn't stop. All the rest of them that went through it stopped. It's really a line that intersects a circle in 2 points. We would call that, line FH. Two tangents. A tangent is a line that lies in the plane of a circle and intersects the circle in only 1 point. So one tangent line is line. We want arrows on this one. Line EY. Its point of tangency is point E. And you can identify the other tangent line and its point of tangency. Okay? We're going to let you name the sphere and its center and chords and secants and tangents and points of tangency. We want to circumscribe a circle about the triangle. Circumscribe a circle about a triangle. We ever heard of that? Well, yes, on Theorem 5.8. We need something, if we're going to circumscribe it about the triangle, we need a point that is equidistant from the vertices. Now, how do we get a point that is equidistant from the vertices? Well, Theorem 5.8 says that the perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the 3 vertices of the triangle. The perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the 3 vertices of the triangle. Now, here's how you get a perpendicular bisector. You take your little compass thing. Give me just a second to reorient my board. Okay, to make a perpendicular bisector, you're going to take your compass, that's your circle drawer. You're going to take the pointy end and then the pencil end. You're going to make sure on your pencil end you go over halfway and you're going to make an arc. You're going to leave it open exactly the same amount. Put your pointy end here, pencil in there. It'll be over halfway. You make an arc the same. You find the 2 points where those 2 arcs intersected, and you draw a line through that, and that will be the perpendicular bisector of the segment. Now, it may not look like it there because I freehanded that. You're going to do that to all 3 sides. So once you get the perpendicular bisector of all 3 sides, they're what we say concurrent at a point that is equidistant from the vertices. So we can use that point of concurrency, we call it the circumcenter, and that distance as a radius, and we can circumscribe a circle about the triangle. So we're using Theorem 5.8. You go back to Chapter 5 if you need to study that. The perpendicular bisectors of the sides of a triangle intersect at a point that is equidistant from the vertices of the triangle. If we want to inscribe a circle, we're going to go back to Chapter 5. We're going to look at Theorem 5.7. We're wanting to inscribe it, which means that the circle needs to be such that each of the sides is a point of tangency. In other words, the center of the circle needs to be equidistant from the sides. So what point is equidistant from the sides? Well, it's called the incenter. And it comes from a theorem that says the bisectors of the angles of a triangle intersect at a point that is equidistant from the 3 sides of the triangle. So you would have to construct the angle bisectors. To construct an angle bisector, you would take your compass, you would put it on the pointy end on your vertex, you would make an arc with your pencil, and you'd make an arc like that, okay? And then you would open up your compass again, pointy end here, pencil going over halfway, and you would make an arc. You would then leave your compass open the same amount. You'd make an arc the other way. I did a very bad job there. So with our compass pointy end here, we make an arc. With our compass pointy end here open just over halfway, we would make an arc there. We'd leave it open the same amount, put the pointy end here and the pencil there, make an arc there. If we go through those points of intersection, then we will have an angle bisector. If you do that and construct all three angle bisectors, they are concurrent at a point that is equidistant from the sides. So you would have to find straight over 90. That's going to create a radius. And so you could inscribe, the circle in the triangle. Okay? The center of that circle, again, is called the incenter because it is the center of the inscribed circle. Now, we're doing discovery learning here. We're going to inscribe a parallelogram, inscribe a rectangle, inscribe a square, inscribe a right triangle, inscribe an obtuse triangle, inscribe an acute triangle. Let's just kind of play with some of these. To inscribe an acute triangle is pretty easy. You want to go past the center. We just want the vertices there, connect, it's inscribed. There's an acute one. An obtuse one. I don't want to give it all away. Do you see that if we thought about a diameter, if we take a point above that diameter, if we want an acute triangle, we had to pick 2 more points below that diameter. What if we started with a point above the diameter? We wanted an obtuse triangle. Where would we have to put the other 2 points? And then we would think about if I wanted to inscribe a right triangle and I had a point above a diameter, then where would I have to put the other 2 points so that I ended up with a right triangle? Now, this is some discovery stuff, and we're going to let you play with that. But what we're thinking about here is the relationship between the first point and where the other 2 points are located based on the diameter. See? Inscribe a square. How would you inscribe a square? You might think, well, I'm going to start with a point. Good luck. Trying to get those all in the right place so that these are all exactly 90-degree angles and all the sides are equal. You're going to have quite a time trying to get that done. Let me give you a hint. If we drew the diagonals correctly, see, we're still dealing with a diameter, right? If we drew the diagonals correctly, then the vertices would end up in the right place. So you need to think about all the properties of the diagonals of a square, which means we need to go back to chapter 4. Now, a square is a rhombus, so the diagonals are perpendicular and bisect each other. A square is a rectangle, so the diagonals are equal. A square is a parallelogram, so the diagonals bisect each other. And so what we would want to do is draw perpendicular diameters Then we have the properties of the diagonals of a square. They're equal and bisect each other. And if we do, then when we connect that, and I didn't do a good job again, but anyway, if you actually make these perpendicular diagonals, you're actually going to get a perfect square, okay? Because we're using rules of geometry, definitions, postulates, and theorems to make our decision on how to do it. We're not guessing, you see. All right, so this is not a page of guesswork. This is a page of logical thought process where we know exactly what we're going to get as we think through the properties of geometry, okay? All right, so that's the end of